43 PV, and we're going to talk about inverters today, but I'm just going to open up for questions first. Are you guys all set for quizzes, exams, assignments? Is that rolling along? Okay.
What do you mean are they?
Well, I know you were behind on a couple of things because of a family emergency, but is everything open though? I mean, that you need to be open? Okay, I think I opened up everything last week, so. Yeah. All right. And then I also want to say, like, I'm more than happy to do this video conference if, because I think Doty's in here, but if not, and I apologize. I did not put my. I might be a couple weeks behind on posting the lectures, but I'll be sure to do that for this week. So, okay. Inverters. Let's just kind of walk through the content together. I'll highlight a few things. Might have to wrap up just a little bit earlier today so we can get to that 12 o'clock meeting. I just want to hit the highlights on this. Okay. See if we can read it on the screen here. Actually, no, I'm just going to go ahead and download it. I thought the machine was going to run a little faster today. Come on, you know. Sorry. Documents, courses. And this is also something I suggest you do. You've got this, you've got all these great PDFs in the course shell. You've got a hard drive on your computer, and well, I just suggest organizing them. So I organize in a couple different ways, and I guess I'm guilty of not doing this, but I do it by year, but I would also suggest organizing by week.
The course or year that the...
Year of the course, like so 2010, 2011, etc. That's going to have like grades in it and individual assignments, but what I'm doing right now is making a folder. It's just called Week 8 Inverters. Open. Might be time for a new laptop. Open. Save. Whew. I don't know why it's so slow. Man. It's getting full. Nah, we'll go back. Okay, so anyway, we'll go back out here. Courses. Yeah, man, wow, super slow. Okay. Week 8. Okay. So there's 8 pages to this guy. Man. So source circuit. Source circuit just basically means the source, so the photovoltaic source, where the sunlight is coming in and being turned to electricity. Most important aspect of PV design, the electrical and mechanical characteristics follow from this fundamental design decision, which is bearing on both labor and material costs. So the idea is to get your design together up front so the laborers can come in and put the thing together quickly. What was the statistic that like a new PV array was going in every 4 minutes in the U.S. A couple of years ago, and what used to take almost a week, you can have a crew come in and have a PV array installed in half a day, 4 hours. Three-person crew, 4 hours, and you're done. Okay. So low DC array voltage, for example, is a common cause of substandard performance when you've got open circuit or operating voltages for an array that meet the minimum inverter DC input. So we talked last time a little bit how to charge a battery, obviously the voltage has to be greater, the charging voltage has to be greater than the battery voltage. Same thing going into your inverter, and again, in any PV array, you're going from a DC current that's coming out of the array into your AC if you're grid tied. That said, there are now some 12-volt standards coming out for U.S. residential. There's a guy in Billings just took his house off grid, and they're sort of rewriting that so you can actually avoid the inverter in some cases because you're going to lose some electricity there. Okay, in this article I detail array design best practices for determining the maximum number of modules in a source circuit. You also don't want to put too many. So it's a Goldilocks problem. Too few, you're not going to make your voltage too many and you're going to blow the system. Okay. He's also referring to the National Electrical Code. To my knowledge, Montana is still on the 2011 code. It's published every 3 years. There is a 2014 code. It could be this year that Montana does finally adopt the 2014. There typically aren't that many changes, but with all the new things we're seeing in PV, I'm sure there's new things in there that Montana will catch up with. Okay. So he says, while these may be more conservative than current design standards, which you're going to find in the code, my opinions are based on years of experience. And that's always going to be the case. I mean, you kind of have to do it by the book, but the book is not going to prescribe exactly what to do. It's just going to give you some limits. This guy is using his own experience to dial in best practices. Okay. See if I can make this a little bigger. Yeah, so this is true. A lot of times too, when you're going to put in a PV system, you're going to need an electrician to actually do, a licensed electrician to do the wiring. So frequently there are several suppliers involved. Someone's making the inverter, someone's making the panels. It's not always the same someone, but the point of the energy technologist is to get those two systems to work together. Yeah. So here's a deal. We were just talking about Apple versus PC, and you might have a conflict of interest where the best system design might be the panels from one company and the inverter from another, but if someone's there trying to sell you their inverter, they might be also pushing their modules. So that's what he means by conflict of interest. Okay. This is avoiding the pitfalls of string sizing on autopilot. This basically means put some thought into it. All right. This afternoon, Tim, Chester, and I are actually going to head over to the Hive because we've got some really old thin film PVs, and we're looking for somewhere to put them. I don't think they're going to go on the new building, but we might run them up to Browning. My concern is exactly this, that the things, they might work, but they're not actually going to make enough current to make much of a difference. So we're going to hopefully test those today. The problem is right now, if we went out there with an insulation meter, we're probably down around 400 to 200 watts per square meter, well below that 1,000 watts per square meter standard. We talked a little bit before about MPP, and if you remember, MPP is just so power is the product of current and voltage, and you can see for each one of these different solar intensities, the power is going to differ. So at let's just cruise along this 200 watt per square meter curve. And let's just call this 1.5 amps. 1.5 times 20, this would be 30 watts coming out. 1.5 times 25, what is that? 25, 37 and a half watts. By the time you get out here, though, you can see if I went all the way out here to this knee, now I'm talking 1 amp, 30 volts, and now I'm back down to 30 watts. So somewhere in between that 37 and that 30 is going to be the maximum. And so the MPP is always, regardless of the power coming into the array, is trying to find the sweet spot in that knee of the curve. So that's that. Now, the maximum DC voltage for an inverter is clearly stated on the product spec sheet. So the point is, you don't want to have so much voltage coming into the inverter that you're outside the spec. It says the maximum voltage is generally set by the input capacitors and the ratings of the transistors on the inverter. So it's a constant rather than a variable limit. Because it is possible to create an overvoltage in an inverter by putting too many modules in a series, like in series, in electrical series, some manufacturers keep the maximum DC input voltage in non-volatile memory for warranty purposes. This allows the manufacturer's service technicians to verify the maximum DC voltage input to any inverter that is returned from the field under warranty. If it was exposed to overvoltage, then the manufacturer may choose not to provide a free replacement. So the inverter manufacturers themselves will be able to determine if it was the fault of the installer for loading it up too heavily. Okay. Low design temperature, that's coming here in a few pages. So it's also, this is just for 25 degrees Celsius. If the temperature lowered, each one of these curves would rise. If the temperature got hotter, each one of these curves would diminish.
Do most cells include a optimal operating temperature as well as?
Well, all the standard is 25 degrees, 25 degrees Celsius, and so that's what they're rated for. And to my knowledge, every single array is going to become more efficient when it's colder and less efficient when it's hotter. And and it's not going to be linear necessarily, but I think it might be maybe a 1/10% per degree is about the efficiency. And so just a couple of years ago, we tested that by putting in some 2-watt computer fans and just blew ambient air over the panels. And so we actually it was kind of strange. It was just to actually see this in operation, but we put 2 watts from the system into the fans and got 4 watts back out. Yeah, just by cooling them with their own electricity. It was pretty wild to see, to see it as soon as you plug it in. And I've always had that same question. I mean, you see people sometimes fanning themselves on a hot day, and you're wondering, are you putting more? Is Is more energy coming from your hand? But if you look at the math, though, I think your brain, usually you're cooling your head off, right? Because your brain is sitting there cooking inside your skull. But your brain, which is something like 3 to 4% of your body mass, is consuming almost 20% of its energy. So it could be that just this little flick of your wrist actually is dissipating more heat than energy it's consuming. So, yeah. Yeah. Oh, here's another thing just to keep in mind. There's a dry bulb temperature and a wet bulb temperature, and the difference there is that the dry bulb obviously does not have any fluid surrounding it, and I had this exact same conversation with a geoscientist a few weeks ago, where, did I tell you guys this? The stone, yeah. So this is a good one. We're sitting there, actually in the lobby at the hotel in Browning, and there was a. Let's just pretend this is natural stone up here, the whiteboard, and this is some kind of concrete composite. Well, he said, I won't name any names, he said that the stone is colder than the concrete because, he says, you can always tell if it's natural stone because it's colder than the concrete. Well, what he's arguing somehow is that two objects in the same room somehow have different temperatures. That violates the 0th law of thermodynamics. It says if the air, so the air in this room is in contact with this board, so it's in thermodynamic equilibrium with this board. So they're at the same temperature. The air in this room is also in contact with this. So all three temperatures are the same. That's the 0th law of thermodynamics. This one feels colder because it's smoother. There's more surface area to conduct the heat out of my hand, which is hotter than the board, and there is this other surface down here that's it's a fabric, sort of like the porosity you'll see in concrete. So they're the same temperature. So back to the wet bulb, dry bulb, and the example I gave him, I said, well, if you're up filming the movie Revenant, and it's 32 degrees in the air and it's 32 degrees in the water, where would you rather be? You would much rather be in the air than the water. They're the same temperature, it's just the heat transfer coefficient is different. And so the wet bulb, dry bulb takes that into account. And I don't want to get too far into that, but if you ever see that, later, there's always a wet bulb temperature and a dry bulb temperature, and a few years ago, and they're actually used to calculate what's called the apparent wind chill, the wind chill factor. That's always up. What's the wind chill? Well,
RH too.
Yeah, and relative humidity as well. Yeah.
They have this. That's what at least they used to use on fires and stuff.
Oh yeah.
And that's how they sling the weather. They call it.
Sling the weather, right? Exactly. Yeah.
Spin them and then take the measurements off each thermometer.
Yep.
And there was a chart.
Yep. Yeah, it's exactly right, because you'll in that swinging, you'll have a wet and a dry bulb, and if you have a higher relative humidity, it's going to conduct heat towards your body faster than if the humidity was lower. So same thing with being in cold air versus cold water. Yep. Super. Okay. Yeah, this might be worth looking into. Expedited permit process for PV systems documentation, solar ABCs. Okay. Here's another thing to consider. Shorter source circuits. We spent a lot of time when we were putting this West Campus solar initiative together to figure out how to reduce the size of the length of the wires. A couple reasons. One, it's longer wires more expensive, but also you have more losses. So if you're so since the temperature affects the total voltage coming out of the array, that's yet another thing to consider. How far away the panels are from your inverter, because that'll drop your voltage as well. Okay. So
How
let's keep.
far does it really start to, how far away before it really
Yeah.
starts to limit?
Yeah, we haven't done them yet, but for every wire gauge, you have so resistance is measured in ohm centimeters, and so the length actually will tell you how many ohms you're going to lose, and then you run that through your P equals I squared R, and that'll tell you how much power is being lost. And every single wire has that. But we'll get to that. That's coming later in the course. Yeah. So how far is too far? Well, it depends on a lot of other factors. How big the wire is, and again, temperature, just like we're looking. Okay. So it says proceed with caution. While the extreme annual mean minimum design dry bulb temperature data published by ASHRAE are generally statistically valid, more conservative data may be required for higher altitude. I don't know what this very well could be somewhere in Montana, in fact. Okay. All right. So what these guys are actually looking at, let's just take a look at this little figure. The set of IV curves in figure 2 assumes source circuits, so evergreen, 195 modules, 20 circuits applied and connected in parallel. That's a lot. SATCON PVS inverter with a 305 voltage DC MPPT. So we're looking, let's see what 305 is. Right here. Okay, so what's the issue with this thing? This is the ASHRAE low design temperature is 0 Celsius, and the ASHRAE 2% design temperature is 45 Celsius. So as you climb up that temperature, 45C is pretty hot. That's up in the hundreds. The latter results in a minimum array operating voltage of 298. So we're actually below the place where that MPPT is happy. So there you go. On the hottest days of summer, when the solar resource is greatest, the inverter is unable to operate the array at its maximum power point. Not always a big deal in Montana, but sometimes we'll hit 110 Fahrenheit. So what they say here, the best array design is actually 16 modules per source circuit, which results in a minimum array operating voltage of 305.
So when they say circuit, I'm assuming they mean like a
Circuit of panels. Yeah, an array of panels. Yeah, exactly. Yep, that's exactly what they mean. So each module, again, is just what we call a panel.
made up of several cells.
Mhm.
To achieve that voltage, you have to.
Right, because each cell itself is like a half a volt. Right,
Yeah.
yeah. Right. Oh, And another thing to consider is that panels will lose performance over time, and they're typically rated that they're going to lose 1% per year. Yeah, and so you have to take that into account as well over the lifetime of the panels. No technology lasts forever, and it's not going to be linear either, but they're almost always listed with a sort of percentage loss of function per year.
Is that just materials degradation, basically?
Yep, it is. And really what's going on inside, and we've talked a little bit about how the individual crystals of silicon are aligned. Anytime you've got a material that's undergoing some kind of thermal cycling, hot, cold, it cracks. There are no self-healing silicon panels that I know of yet. Maybe somewhere down the road. There's a Dutch engineer just came up with self-healing concrete, where he's got a bacteria that lives in there and secretes calcium carbonate that puts the thing back together. But we do not have self-healing PV panels. So, as those things get hot, cold, just the little crystals themselves break apart, and you can just think of the cell as a wire or a battery or a component. The more cracks that develop in there, the fewer paths there are for the electrons to flow into the copper. There's a whole thing, if you wanted to really get into it, it's called percolation theory in the literature. So how lots of different particles move through systems. And we did a little bit of that last time with the battery. Remember, bodies moving into the auditorium. It's easy first, and then it's hard later. So kind of the same deal. But the degradation is thermal. So at a minimum, that's a minimum. I said 1 to 1.2, a loss of 5% per year, 0.5% per year. And again, where does that 0.5% go? Well, some of it goes to voltage and some of it goes to current. Yeah, so 25 years you might lose 6%. All right, what else is in here? Yeah, and hopefully if you get into this field, these are things that you're going to learn on the fly anyway. You're going to be working under somebody who's done these calculations with specific panels before. They should have data, actual field data from arrays, and there are a lot of applications out there right now where you can get real-time feedback. So on a cold day, you can see what's going on. On a really hot day, you can also see. So if you do end up going to work for a PV installer, I would try to get on the ground floor of some of this stuff and understand when the systems start to fail and why, because that's what's going to keep the customers happy. The systems that work.
Is it very common for there to be intelligent algorithms that will just adjust your panels on the fly? That's on the residential scale? Well,
one thing, most of what we're reading right here is for one large inverter. There are a lot of micro inverters now, so each panel operates independently. They're more expensive, but like you said, they're a little more robust. Because if one panel or module goes down, it doesn't take out the whole system. So the micro inverters have made a pretty big impact on that field. So they can,
We had a slight visit through that solarized Missoula.
Nice.
And that's kind of what we figured out. We just would have different inverters.
Do the micro inverters?
Yeah.
Yeah.
So that if the system does go,
if one panel goes, you don't lose the whole
still
system.
making most of your
Yep.
energy.
Yep.
If you just have one, then it was for the whole system was only about $400 more to do that.
Yeah.
So,
Theoretically, that could just mean more efficiency overall, so you're making your money back for the next few years. anyway.
Yeah, that sounds right. You know, typically it is, money spent up front can save you money down the road.
yeah.
Okay, we'll take a break there.